In the previous course, we have designed a low-pass filter which has a cutoff frequency of 100 kHz, right? We chose this frequency in the belief that this will be good enough to remove this 500 kHz noise signal. But how do we know if our filter has any success in removing this noise, and how do we know that our filter doesn't attenuate the voltage of this audio signal? Well, let's find out. We can calculate the theoretical behavior of a low-pass filter by using a frequency-dependent version of a typical voltage divider calculation. The output of a resistive voltage divider is shown here. If you don't remember this equation, please check the voltage divider course that can be found in the first chapter. The RC filter uses an equivalent structure, but instead of R2 we have a capacitor, right? First, we replace R2 only in the numerator with the reactance of the capacitor. Next, we need to calculate the magnitude of the total impedance and place that in the denominator. As a result, we will get this equation here. The reactance of a capacitor indicates the amount of opposition to current flow, isn't it? But unlike resistance, the amount of opposition depends on the frequency of the signal passing through the capacitor. As a result, we have to calculate the reactance at a specific frequency, and the equation that we use for this will be this one. I have to repeat this again, but if you don't remember this equation, please check the reactance course. Now, when we tried in the previous course to design a low-pass filter with a cutoff frequency of 100 kHz, we chose a capacitor with a value of 10 nanofarads, and after a little calculation we got a resistor with a value of approximately 160 ohms, right? We will assume that the amplitude of the input voltage is 1 volt, so that we can simply remove this from the calculation. First, let's calculate the amplitude of the output voltage at the audio signal frequency, which is 5 kHz, right? In order to calculate the output voltage, first we need to calculate the reactance of the capacitor at 5 kHz. And inserting all the values in this equation, we will get a reactance of 3183 ohms. Now that we know this, the output voltage at 5 kHz will be 0.999 volts. The amplitude of this sine wave is essentially unchanged. And that's good, since our intention was to preserve the sine wave while suppressing the noise. When I say sine wave, I mean the audio signal which is present at 5 kHz, right? This 1 volt here is not the voltage of this battery, don't confuse yourself. It's the amplitude of the audio signal. This circuit is here just to help you to understand where this equation came from. Now let's see how successful the filter will attenuate the noise component. First, let's calculate the reactance of the capacitor at 500 kHz, and as you can see, we will get a value of 31.8 ohms. After inserting this value into the equation, we will get an output voltage of 0.195 volts. So this means that we successfully managed to reduce the noise amplitude with about 20% of its original value.